atoms inside this mass will start to go relativistic. They will hit speed of light, they will start moving with speed of light, and basically you will need infinite energy or infinite time to compress it further to a singularity, right? And Einstein argued that, okay, theoretically it might be possible, but physically, in reality, it will not be possible. Until 2 months later, July 10, 1939, exact 2 months later. So, May 10, July 10, right? Oppenheimer and his student, everything is yeah. So basically, Oppenheimer, what he said that a sufficiently massive star will actually be able to compress even further. It will be able to collapse even further. So Einstein is wrong, and he was able to show this using some field equations. And I'm not exactly sure what happened, but yeah. So he basically said that okay, it can actually collapse further than what Einstein is saying. Yeah. So stars were like, okay, finally we can become black holes. But even this did not clear out the confusion. Up until 1965, when Roger Penrose said that this gravitational collapse will inevitably form black holes. Right? He basically went on to prove this, and he actually got the Nobel Prize for this in 2020. So that figure on the right, that is what won him his Nobel Prize. Right? And yeah, so a collapsed star will actually form a black hole. And then comes Hawking in 1970s. Right? He gave us the area theorem, and he also gave us the Hawking radiation. And he was like, okay, so now we have entered the modern realm. People have kind of accepted, okay, these black holes can actually exist, they might exist, but still detection was a very long way off, and we did it. In fact, we imaged them as well. This was the first image of the black hole that was ever captured. The first time that we could see the black hole with unaided eyes. This is credited to the Event Horizon Telescope collaboration, and this was the image of a supermassive black hole at the center of Messier 87 galaxy. Right? And this came out in 2019. And in 2019, we were not able to actually see the black hole. Now, what are the different parts of a black hole? Let's go back to this image. Right? And what are we actually seeing? Because we know for a fact that we cannot actually see a black hole, right? There's no light or radiation coming from it. So what are we actually seeing? This central dark spot that we see, that is the black hole, the absence of light. Just close all the lights. So this central dark spot that we see is right. So this central dark spot is the black hole, basically the absence of light, and all the orange that you see, that actually is light or radiation coming from the accretion disk surrounding the black hole. So we are actually not imaging the black hole, but the surrounding material which gives us the presence of the black hole. Right. So this is very hot plasma that is radiating in X-ray and radio. And that is what we are actually imaging using the Event Horizon Telescope. Now, what are the different parts that we can actually identify in this image? So, you might have seen Interstellar, right? I think everyone has seen it by now, right? And in fact, this came out in 2014, and this was a huge predictor of how actually black holes will look like. They did computer simulations and gave us an image of what black hole might actually look like. And this was actually pretty accurate, right? So we'll see what are the different parts to a black hole that we can identify. First, there's a singularity. At the very center of the black hole, right, there's a singularity, a very infinitely dense point. It's smaller than a pencil, I don't know. It's very infinitely dense, very small. Then you have event horizon, right? So any matter that falls will never escape. Then you have something called a a photon sphere, right? It's a glowing ring of photons, which only you can only see because the gravity is so immense that it bends to light, and you sort of see a glowing ring. So if you go back to this image of the black hole, so this inner ring of light that you see, that is the photon sphere, right? And this only happens because light, all the light is bent in such a way that it forms this circular ring of photons.
Like, does it mean like light is orbiting?
Yeah, so somewhat like light is orbiting, photons are basically orbiting the black hole, right? Then we have something called relativistic jets. Yes?
You should not be able to see the light.
Sorry?
Should be a light like that.
Yeah, you should actually not be able to see your photons still, but there are parts to it, right? So I can actually tell you more cross-sectional thing that okay, these are the parts to a black hole. We are not actually seeing the photons still. It was just a representation in the movie as well. So if you go to the actual image, you do not see the photons there really. You actually see the accretion disk there, right? And then the black hole you see. So yeah. Then we have something called relativistic jets. So whenever a lot of a black hole accretes a lot of mass or gas, stars, or any material, a lot of it is ejected in a very high energy ways, in very high energy jets from the poles of the black hole, right? And these are so highly energetic and so bright and they are so large that they can span light years, right? And this is one of the most prominent ways that we actually detect black holes. So relativistic jet, and the other prominent thing that is the accretion disk. So accretion disk is actually a hot disk of plasma that is kind of orbiting around the black hole. It has not infall. It is not infalling. It is orbiting the black hole. Right? It will slowly infall, and this is so superheated, and this is highly radiating. You get X-rays, you get radio waves from this, and this is what we actually imaged in the actual images that we see. And yeah, so this is a more complete picture of what I was telling you with all the other details, right? So you have the singularity, you have the event horizon, you have the photon sphere, the singular ring of light, you have the accretion disk, and the relativistic jets. My drawing is not that good, so yeah. Anyways, now what kinds of black hole do exist? Right, in our universe, what kinds of black holes do we actually see? The first one is the young, carefree, stellar mass black holes. Right, these are the most common type of black holes, right, which are formed at the end of a star's life cycle. So, due to stellar collapse, right, after the stars have collapsed, and these are usually typically in mass range of 20 to 30 times the sun's mass, and in fact, these are so common that we believe that billions of them exist in our Milky Way galaxies. They are scattered all around the galaxy, right? Now, an interesting thing about these black holes is that typically they are found in binary systems. We do not see them isolated. Any cases why that might be the case. Sorry? Okay, might be one reason.
One star like attracts the other star mass.
Okay. Yeah.
A hole has two sides.
Sorry?
A hole has two sides.
Okay.
That's it.
Okay. Yeah.
Because binary star systems are the most common form in black holes.
Binary star systems are not strong. Okay, that is kind of a reason, but no. Your reason was sort of there. So actually what happens is the binary systems are very common, right? And when in binary systems we have two stars orbiting sort of each other, and when one star becomes a black hole, right, it it starts to capture the other star's material or the gas that is inside the other star. So this is what happens in a binary system. Right? There's a companion star, there's a black hole, and it starts to accrete all the material from the companion star onto itself. It will fall, it will make accretions, it will have jets of its own. But the reason why we typically find them and not wandering or isolated ones is because for detecting black holes, we need surrounding material. Isolated black holes cannot form accretion disks because they are sort of isolated, they do not have enough material around them, right? So to detect them, we need something infalling material. We need an accretion disk, some jets, and that is why we typically find that these mass black holes exist in binary systems, right? Because that is an observational constraint that we have. There can be many of them that are wandering, can outnumber these binary systems by millions, and we'll never do because we cannot actually observe them right now. And that is an observation list. So yeah. Chicken and the egg top. Which came first? The galaxy or the supermassive black hole? So we discussed more about this, but just remember, virtually every galaxy that we have ever seen has a supermassive black hole that we see. And then the growth phase, like we do not know where they come from, but we do have an idea of how they evolve and grow in their host galaxy. Right? We'll come to this later. It's very interesting. Then we have the missing middle child, the intermediate black holes. So we have seen 20 to 30 times, right, the size of the sun. We have also seen billions times the size of the sun, right? But we do not see many of these intermediate masses, right? So we have no idea how they make, right? The masses can be from 100 to 1000. No one has any idea. But whenever we do observe them, we are sure that they did not form by collapsed stars, because stars have a limit of how massive the black hole can be. Like due to stellar star's evolution, there will be a limit on black hole mass. So we are sure, okay, they did not form due to collapsed stars, but they're not also as large as supermassive, so we cannot group them together. Right? So the possible ways, right, that people think they might have formed are probably a product of multiple black hole mergers. They have merged with multiple black holes, and that is why they are so massive. Or maybe a completely different process. We don't know. This is work in progress. Right? Now, what can the black holes actually tell us? Right? We have seen the parts of the black hole, the history of the black hole, what kind of discussions have happened. Right? Now we dive into the astrophysics a little bit. We'll stay away from the history. And what can black holes actually tell us? So coming back to the supermassive ones. So supermassive black holes exist in galactic pools. Right? And again, we do not know whether the galaxy came first or the black hole is in a big problem. Right? But what we do know is that these black holes interact very closely with their host galaxies. Right? They affect their host galaxies a lot. And how do they actually affect this? There's something called AGN feedback. Right? So galaxy evolution, formation and evolution is affected by these black holes. Something called AGN feedback. Now, let's understand what AGN feedback actually is. So when there's a black hole and there's a galaxy surrounding it, a lot of matter is actually infalling into the black hole, right? Can we agree to that? Can I have a yes? Yes, right. So a lot of matter is actually infalling into the black hole, right? And when this matter infalls, the black hole's mass increases, its gravity increases, and it will attract more matter towards it, right? Now it's accretion rate. So accretion rate is basically mass by time. How much mass is infalling by time. Its accretion rate will increase because its gravity has increased. It will attract even more matter. But we have seen that these black holes have an accretion disk around, right? They are radiating a lot of energy as well. So more matter they accrete, the more this feedback energy, this energy is radiated back into the galaxy as well, right? So this black hole, it will accrete a lot of mass, it will output a huge burst of energy, it will heat up the surroundings, and when the surroundings get heated up, when they are heated, what will happen if you heat the gas? It will sort of become more dispersed, or gas disperses, right? And it will stop falling inside the black hole. It will be tougher to get dispersed gas back into the black hole. And this process of infalling material, feedback energy going back into the galaxy, and that stopping the infalling material, this sort of acts as a black hole growth regulator. So growth of these massive black holes is regulated by themselves, by the energy they are pouring back into the galaxy. Does that make sense? Right? So also what we see is more massive the galaxy, more massive will the black hole be. Right? So more massive the galaxy, more time the black hole has spent accreting a lot of material, and it will be more massive. And the feedback energy is also more massive for a more massive, more bigger, larger for a more massive black hole. It's outputting even more energy because it's taking in a lot of material, right? And this drives the galaxy evolution. All this heated up material, right? All the material that gets heated up, this drives the galaxy's evolution because this is happening on a very large scale in the galaxy, right? And this suppresses the star formation in the galaxy. So after a point of time, stars will not be, the galaxy will not form as many stars. In fact, you can actually see, sorry for putting a graph in this talk, but you can actually see suppressed star formation in massive waves, right? Equally extreme. The y-axis is the stellar mass amount of stars present in a halo, and the x-axis is the halo mass, the mass of the galaxy, total mass of the galaxy, accounting for gas, dark matter, black hole, etc., etc. Right? So stellar mass versus halo mass. Now you will see this scales really well. There's a kind of a, it's a log linear, it's a log of what. So this is kind of exponential. Right? You see an exponential growth with like halo mass increasing, stellar mass also increasing side by side. Right? But suddenly, near 10 to the power 12 to 13, you see a sort of dip. All these lines are different ratios. So just focus on the black and now. They sort of see a dip at this particular mass scale, where they have stopped forming stars. Right? They're not galaxy. The galaxy is growing. It has a lot of material, but it is not forming stars. Right? So we do see suppressed star formation in more massive halos. Now it is still like people are still arguing whether it happens because the galaxy has grown way too massive and it's not able to form stars that efficiently, or is it because of the black holes? Yes.
What are the different values of Z?
So the different values of Z correspond to different redshifts, right? And basically what this paper did was it used observational data, simulations, etc. to constrain and give you the stellar mass relation at different redshifts. So they used a variety of data and constrained, fitted, best fitting. They gave some parameters which they used for fitting, and then they gave these curves just for fitting these stellar mass relations for galaxies at different dimensions. Right. So yeah. Now, right. So what you actually will see is peak kilomass is I think from dynamical mass or something. And you can see where else these are present. And they used a laser interferometer to actually measure the gravitational waves. Right here, right here on. Now, this is the more interesting part of gravitational wave astronomy. So this is stellar radar. I'll quickly explain what it is. This is a representation of all the typical kinds of motions that we have seen lately from all over the place, right? So now you see that these intermediate mass black holes have started showing up, 100, 200 times the mass of sun, solar masses, right? These have started showing up. So gravitational wave astronomy gives you a new way to probe these intermediate mass black holes, right? And now you can actually observe or basically see them merging and kind of have an idea of their origins. You can study their origins, how do they form, where are they coming from, right? And this mass gap between stellar mass black holes and supermassive black holes can be sort of, yes? X-axis is nothing. It's just spread it all over the place. So you can actually see it better. So X-axis is not representative of anything. So what is happening here? I'll quickly explain. So they have two different masses of these black holes combining to form a bigger mass. So these arrows, all these arrows that you see, these are mergers happening, right? And you can sort of see, okay, how are these black holes sort of growing up, right? We haven't detected multiple mergers yet, but yeah. So you basically now you have an idea or how these intermediate mass black holes will form, right?
What are that
EM black holes is, I think, ones that have been seen in EM counterpart systems. So we have black hole data and also as well the EM, basically the host galaxy data, right? So whatever they can match with a host galaxy, they call it a EM black hole, right? So they're saying we have a host galaxy for this particular black hole. Any other questions? Yes.
How are the neutron stars formed when they are even less than the mass of the sun? Like here we are seeing here that neutron stars are there of one solar mass to two solar masses.
So neutron stars form at the life cycle end of the black hole. So sorry, not black hole, stars. So there are certain mass constraints and stuff. Right, I'm not the expert on that, but there are certain mass constraints on the star's mass, and if then it reaches the particular end of its own life cycle, based on its mass and type, it will sort of evolve either into a white dwarf or a black hole or a neutron star. I think, yeah.
I'm not sure. I might be wrong, but you don't have a object of one solar mass cannot become neutron star. It's not like that.
Yeah, I'm not
Radius
sure.
will be much smaller. Neutrons must be very small.
Yeah, so there are some constraints. I'm not familiar with this stuff. So is for completion. Right. Anyways, moving on. We also have primordial. Yes.
In the previous slide,
Yes.
there were few reaching out to above two, there are few circles which are part blue, part orange, like part neutron star, part.
Yeah, so those are actually neutron star black hole mergers. We also see neutron stars and black holes merging in LIGO, and that is what those mergers kind of represent. Any other questions? Alright, we'll move on. So, primordial black holes, right? It has been theorized that there's something called a primordial black hole, which formed like within quintillionth of a second after Big Bang happened, right? So in very, very early universe, and purely because of density fluctuations in the early universe. So these primordial black holes could have ranged from like somewhere around the mass of a sun to billions of times, right? And these are theorized. I do not know anything about them except from what I've read about, right, in brief. So again, they formed very early, and they can serve if we study them. NASA has a mission for this. If we study them, we can kind of probe the early epochs of the universe, right? And that is a very interesting thing to actually see. Scientists say that they might have evaporated by now, right? So it's very tough to actually say if they exist in the past, right? Then another reason why to study black holes is because of the technological advancements that they give us. Right? We have the upcoming NISER mission, which is basically a laser interferometer in space. We'll have 3D orbiting lasers and stuff, right? And we also have Event Horizon Telescope. These are desperate attempts to study the black holes, has pushed the technology to a very good pace and given us such collaborations, such technological advancements. We have made strides in how to process data and theoretical understandings as well. So, all in all, these are the few reasons on why we should talk about black holes. Right? Why are they important? Because they tell us about galaxy formation. They give us a lot of information about that. They help our theoretical understanding of our own laws of physics. Then we are pushing our own boundaries by creating such technological advancements to study them. And that concludes my talk for today. Like, why talk about black holes?
Do you have any questions?
Yeah.
What are those relativistic bits I didn't understand? Why do they